Hello everyone, let's come to the third subsection, Riemann term of interpolation. Okay, let's review some results before. In the beginning, we know what is the interpolation problem. Now, we are given n plus 1 different nodes, x0, x1 to xn, and the corresponding function values fxi equal to yi, I from 0 to n. And we want to find a polynomial denoted by Pn of degree at most n. Okay, so we can write Pnx by a0 plus a1x plus dots to an minus 1 xn minus 1 plus an xn, right? Okay, in order to determine this polynomial, we need to determine the n plus 1 coefficients. Okay, so if we, of course, we need to satisfy this interpolation conditions, Pxi equal to yi, I from 0 to n. Before we have learned the Lagrange interpolation or the Newton interpolation method. We have to solve this linear system. Remember, we substitute x by each node x0, x1 to xn, and to construct the n plus 1 linear equations like this, and then we can solve this linear system to obtain the coefficients, because the determinant of this matrix is not 0, because this matrix is one-mode matrix, right? So here, because we suppose the n plus 1 nodes are different, so the determinant is not 0. So this linear system has a unique solution, the coefficients. That means there exists unique polynomial Px or Pnx. It's okay for you? Okay, so this is the interpolation problem by polynomials. And of course, now we already know we have two methods to construct or to obtain this polynomial. The first method is Lagrange interpolation, right? So here, okay, I use this figure, okay, to show you. Okay, so for example, we are given 3 data points, x0, y0, x1, y1, and x2, y2. We need to find a quadratic polynomial, P2x. Okay, so we want obtain P2x directly by this form. That means we choose 3 new bases, the quadratic Lagrange interpolation bases, L0x, L1x, and L2x. Then we just need to multiply each basis by the function values y0, y1, and y2. Of course, we need to obtain these 3 bases by the interpolation conditions, and we know the figure, right? It's okay. Remember the figure of the 3 bases. And actually, for the general case, here we come to the general case. We can obtain the basis directly by this ratio. This is Lagrange interpolation basis, right? Okay, so x minus x0 multiply to x minus xj minus 1, then jump to x minus xj plus 1, and multiply to x minus xn. This is numerator. And substitute or replace x by xj, because here is lj, right? So xj minus x0 multiply to xj minus xj minus 1, and multiply xj minus xj plus 1, and multiply to up to xj minus xn. This is basis function ljx, right? And then we can obtain the polynomial Pnx by the summation, multiply yi to each basis Lix, right? Okay, so this is a Lagrange method to construct the interpolation polynomial Pn, and we already know the disadvantage is if we add one more node, we need to obtain construct the polynomial the basis totally changed, right? Okay, so later then we have learned the second method. Of course, here is example. Okay, by these nodes we can construct the basic functions, basic polynomials. Okay, and then if we add one node, now you see we need to change every basic function, right? Okay, so in order to keep the formal computation, then we have learned the second method, the Lagrange method, or Lagrange interpolation formula, right? The difference is to choose another set of bases. Okay, so here I show you just to review that review. Okay, so here then we construct Pnx by another set of bases 1 phi 0, right? Phi 0, and phi 1 is x minus x0, phi 2 is x minus x0 multiply x minus x1, and this is phi n. It's okay, remember we only need to add one term if we add one node, and here the coefficients are the divided difference, the nth order divided difference. Okay, so in order to obtain this coefficients, we need to use the divided differences table like this. Remember? Okay, also we have practice by the example here. Okay, or another. Okay, like this. We are given 1, 2, 3, 4 data points, so we need to find a cubic polynomial P3, right? And then we use the table, and we obtain 4 coefficients. Then we can obtain the polynomial directly, right? It's okay. And of course, you shouldn't remember because the interpolation polynomial is unique. So if you choose, if you use Lagrange interpolation method or you use Lagrange formula, you will obtain the same result. It's okay. Okay, so this review something about the interpolation method. Okay, now we come to the remainder term or the error, because we just use, that means we just use Pnx, a polynomial, right, to approximate the function by we just use several discrete points, right? So the question is, what is the error? What is the error or the remainder term? Okay, so this subsection we focus on the remainder term. Here I show you the result. If fx is n plus 1's differentiable function in the interval AB, and we choose the nodes x0, x1 to xn, here we use k plus 1 nodes in the interval AB. Then for any variable x in the interval, there exists Xi also in the interval, right? Bigger than a and less than b, such that, okay, Rn is okay, here it's better to use n, not k, because we use n here. Okay, so Rn is an error, so it is fx minus Pnx. So here also means the remainder term. Alright, it's okay. So we can obtain the remainder term by this form. It is a ratio firstly here. The numerator is the n plus 1's derivative of f at c, here c, and divided by n plus 1 fraction number, and multiply omega n plus 1 x. Okay, we already used before this formula. That means w or omega n plus 1 x equal to x minus x0 multiply x minus x1 multiply to x minus xn. So here you should know we have n plus 1 terms, factors. So it is a polynomial of degree n plus 1. So that is why we write the subscript by n plus 1 means the degree. Okay? It's okay for you? This is the remainder term. It's okay? Okay, so that means, of course, this is a theoretical result. Here, actually we don't know where is the exact c. We only know there exists c, right? So this is a theoretical estimation. Of course, I will explain you later, okay, what's the meaning about the remainder term. But now I show you the proof firstly. Please follow me, then you will also familiar with the divided difference, the properties of divided difference. Okay? So now for any x in the interval AB, okay, if x equal to x0, x1 or xn, that means if we just consider the nodes, then we know the error or remainder term is 0, right? It's okay because we know fxi equal to pnxi, and I from 0, 1 to n, right? So that means fxi minus pnxi equal to rnxi equal to 0, right? Okay, so here you see xi minus x0, xi minus x1, xi minus xn. At least one term we have xi minus xi, so it is 0, right? Okay, so that means if we just consider the nodes, then the remainder is just 0, right? So this formula is satisfied. So now consider one node, then that means if we just consider use fx0 to approximate fx, then this is the error term. It's okay? Clear? If we just use one value fx0 to approximate fx, of course the error is big because you only use one point, right? Okay, continue. Let's continue. Okay, here we consider the k plus 1, okay, k plus 1 order divided difference. Now we have k plus 2, because here x0 and the next should be x1, right? x1 to xk. So we have here k plus 2 nodes. That means here should be k plus 1's order divided difference. It's okay? Okay, by the definition, remember the definition, then it is also a ratio. The numerator is the difference of k's order divided difference. That means we need drop one node. Okay, so here we choose x0 to xk minus 1. So that means we don't use xk here. Okay? And minus another divided difference. Okay, in this case, we don't use x. We only choose x0, x1 to xk. So here you see, we have x0, x1 to xk, k plus 1 noughts. Then this is a case order divided difference. This is also case order divided difference. It's okay? Then divided by. Okay, so remember how to write the denominator. Okay, you should consider the common terms, right? So now you see x0 for both terms. We have x0, x1 to xk minus 1. So what is different? The difference is here. This term, the difference is x. And for this term, okay, here is a difference, right? Okay, different term. Okay, so that means the denominator should be x minus xk. It's okay? Because these are same. Okay? Common terms. It's okay? The definition of divided difference. Okay, continue. If we multiply for both sides, multiply x minus xk here, multiply x minus xk, then denominator is disappear. It's okay? Then we move this term, to the other side. Then we put fx x0 to xk minus 1 to here. Then okay, this term you should know we move this term to this side, so from a negative to positive. Okay, so here fx0 x1 to xk plus this term, so fx x0 dots to xk, okay, multiply x minus xk, so x minus xk. It's okay for you? Okay, so here continue. Actually we just obtain now let's consider firstly, we already know in last slide. Here, fx equal to fx0 plus, okay, the first order divided difference of f at x and x0 multiply x minus x0. It's okay? So here, this term is okay? We put here. And by this formula, let's consider, because this is a general case, right? So we just need to write this term by the new terms, okay? So that means we use this formula. Okay, when choose, okay, here, k equal to 1, then I write, okay, then left side is f x x0, sorry, x and x0. It's okay? Because when k is 1, then here is 1 minus 1 is 0. So we only have x and x0. It's okay? And equal to f x0 x1. You should know k equal to 1, right? So only here x0 x1 plus f, okay, k equal to 1. So fx x0 x1 multiply x minus x1. It's okay? X minus x1. Okay, so here that means we can replace this term, the left side, by the two terms in the right side. You see the two terms. It's okay? fx0 x1 plus fx x0 x1 multiply x minus x1 here. Then multiply this term, factor x minus x0. It's okay? We use this general formula by the case when k equal to 1. Okay, continue. Now, we multiply x minus x0 to these two terms. So first is f square bracket x0 x1 multiply x minus x0 plus this term. Okay, fx x0 x1 multiply x minus x0 multiply x minus x1. It's okay? Okay, then continue. We consider this term with x, x0, x1. So that means for this general term, we consider the case when k equal to 2. Okay, so we use it again. So left side is x, x0, x1. It's okay because now k equal to 2, 2 minus 1 is 1. So 3 nodes, x, x0, and x1. It's okay? And equal to, okay, the first term in the right side, this term is x0, x1, and x2 because k equal to 2, right? So x0, x1, and x2, right? It's okay? And plus, continue. This term, we have x, x0 to xk, k equal to 2. So x, x0, x1, and x2. Then multiply x minus xk, k equal to 2. So x minus x2. See? It's okay? Okay, so that means we can replace this term by the right side two terms. Okay, so, okay, continue. I write it for example. Then we can obtain fx0 plus fx0 x1 multiply x minus x0 plus, now you see, we replace this term by these two terms. So firstly, this is fx0, x1, and x2, right? 3 nodes, multiply these factors, x minus x0, x minus x1. Then plus this the second term. So it is fx, x0, x1, and x2 multiply, okay, x minus x0 firstly, multiply x minus x1. Okay, here we'll have x minus x2, right? X minus x2. See? It's okay? Okay, now let's consider these three terms. fx0 plus fx0 x1 multiply x minus x0 plus fx0 x1 and x2 multiply x minus x0 multiply x minus x1. Okay, now you see these three terms, just the Lagrange formula for the quadratic polynomial. Remember? Okay, let's review it. Okay, now you see, let's come back here. Now you see, fx0, f bracket x0, x1 multiply x minus x0. Here, fx0, x1, x2 multiply x minus x0 multiply x minus x1. It's okay? So that means we just obtain the Lagrange formula. Okay, the Lagrange formula. Here, we just obtain the Lagrange formula. So this terms is just p2x, right? It's p2x. Okay, so now left side is fx. These terms are the summation is p2x. Okay, so that means this is just the error term, remainder term. Clear? So we obtain the remainder term by this form. Clear? Okay, so continue. Actually, we can use this formula. Okay, up to here. Now you see, the first term is fx0 and plus fx0 x1 multiply x minus x0 multiply. Now we can obtain the nth order divided difference. Then here should be x minus x0 multiplied to x minus xn minus 1. It's okay? And plus, okay, similar as this, because here x0 to xn, so here should be x, x0, x1 to xn, then multiply x minus x0, x minus x1 to x minus xn. It's okay? So here is 2, then here is n, and here is 2. Now you say 2 and 2, n and n. It's okay? And then actually, now we know this term, the summation of these terms is just the polynomial Pn. Okay? By the Newton formula, we obtain Pnx. So this term or this term, just a remainder term. Clear? So that means we just use the property, the definition of the divided differences to obtain, okay, we obtain fx equal to the polynomial, Newton polynomial, right? Pnx plus this remainder term. So we obtain remainder term in this form, okay? Okay, so that means Rn equal to fx minus Pnx, then it is just this remainder term. So here, x0 to xn, so here is n plus 2 nodes, so it is n plus 1th order divided difference, right? And multiply x minus x0, x minus x1 to x minus xn. It's okay? So here we just use omega n plus 1x to denote this polynomial n plus 1 degree of n plus 1. It's okay? Okay, so the last step is just to use the property, okay, the relation between divided difference and the derivative. Okay, so we talk about this property before, right? Here, okay, I remind you here. Oh, here. Now you see, if fx is case differentiable function, then here we consider the case order divided difference equal to case order derivative of f at some c divided by case Frank number. And here c between the nodes. Okay? So let's come back here. Now you see, we use the property. So the k n plus 1, because here is n plus 1's order divided difference. So it is equal to the n plus 1's order derivative at some c divided by n plus 1's Frank number, right? C, okay, between the nodes. But here you should know x is also a node, so between x0 to xn. Of course, it means c inside the AB, the interval AB, right? Okay. Actually, this is we just proved the result. Okay, we just proved the result here. Okay. And what's more, I want to show you an interesting fact. Now you see, if we consider the limit, or we consider the nodes are same, okay? In the beginning, of course, don't forget, in the beginning, we need to suppose there are n plus 1 different nodes, right? But now, if we consider the limit, that means if all the nodes are same, x0 equal to x1 equal to xn, right? Then we consider the limit. The limit, okay, now you see, the limit, the derivative of f, the n plus 1's order derivative of f at c, okay? Because here is also a variable. We will only consider these nodes are same, but it is different from x. So here still C, right? Divided by n plus 1's fraction number, multiply then here. Each term is x minus x0. So how many terms here? We have n plus 1's term. So here, power n plus 1. It's okay? Okay, so actually, this is the Taylor's series. Remember Taylor's formula? Okay, I show you again. Because fx equal to fx0 plus f prime x0 divided by one fraction number multiply x minus x0 plus second derivative at x0 divided by two fraction number multiply x minus x0 square plus dots plus 2 fn fraction number nth order derivative at x0 divided by n fraction number multiply x minus x0 power n. It's okay? And plus remainder term, the Lagrange remainder term. Remember, the Lagrange remainder term of Taylor's series is just the n plus 1's order derivative of f at some c divided by n plus 1's order n plus 1's fraction number multiply x minus x0 n plus 1 power. It's okay? Remember, in calculus, we already know this is the Lagrange remainder term of Taylor's series. Okay, actually, if you remember, I also introduce you here the result. Remember, when we consider the same nodes x0 equal to x1 equal to xk, then the Lagrange interpolation polynomial Pn or the same Lagrange interpolation polynomial Pn, okay, then come to the Taylor's series, Taylor's polynomial. Remember here, also here we know the remainder term is also same as the Lagrange remainder term of Taylor's series. Okay, so this is the interesting property between the Lagrange interpolation polynomial and the Taylor's polynomial, also the remainder term. Okay, so this is a theoretical result about the remainder term. Okay. Okay, let's consider an example. Let x0 equal to 1, x2 equal to 4, x3 equal to 9. And we need to find the interpolation polynomial P2 because we are given three data points, right? And then we need consider. Actually, you see, these data points can be sampled from the function y equal to square root of x, right? You see? Okay, when x equal to 1, x0 equal to 1, then y0, I write here, y0 equal to square root of 1, it is 1, right? And y1 equal to square root of 4, so it is 2. And here it should be x0, x1, and x2. Sorry, I need to revise it, okay? And y2 should be square root of 9, so it is 3. It's okay? Okay, so we can find the interpolation polynomial P2 for this function. Okay, and then we can approximate the function value at 3. Okay, and that means we want to approximate the function value square root of 3 to find the approximate value, estimate the error. And we need to estimate the error. Okay, so firstly we consider, that means we can use P23, the function value of P2x, the quadratic polynomial, the function value at 3 to approximate the square root of 3. That means, okay? Okay, so here I show you directly. We use the Lagrange interpolation formula. So here that means, okay, firstly we need to write the basis, right? The basis. Okay, for if we consider the function value, actually this is y0, then we need to construct the polynomial L0x, right? L0x, actually, I just show you the result directly. So in order to help you practice, let's write it in details. Okay, so L0 is a ratio, right? It is x minus other nodes. So other nodes 4 and 9. So x minus 4 multiply x minus 9 divided by, replace x by the node x0. X0 is 1. So it is 1 minus 4 and 1 minus 9. Clear? Then multiply y0. Okay, and here, because we need to use the function value at x3, so that means we substitute x by 3. So here we write 3 minus 4 multiply 3 minus 9 divided by 1 minus 4, 1 minus 9 multiply y0. Y0 is 1. It's okay? This is the first term. Okay, continue. If we consider here, this term is y1. Y1 is 2, right? Y1 is 2. And here should be L1x. L1x, okay, please follow me. It should be x minus other nodes. So x1 is 4. Other nodes are 1 and 9. So x minus 1 multiply x minus 9 divided by, replace x by the node x1. So it is 4, right? 4 minus 1 multiply 4 minus 9. It's okay? Then here, same case, we need to use the function value at 3. So we substitute x by 3. So 3 minus 1 multiply 3 minus 9 divided by 4 minus 1 multiply 4 minus 9. Okay, multiply 2. It's okay? Okay, this is the second term. Okay, the last term for the function value at x2. So it is y2, right? So y2, okay, y2 is 3. And we need to write L2x, right? The basic function, basic polynomial. So it is numerator x minus other nodes. Okay, so here we consider the node x2 equal to 9. So it should be x minus 1 multiply x minus 4, right? Other nodes 1 and 4. And substitute x by 9. So 9 minus 1 multiply 9 minus 4. Clear? Okay, so again, we replace x by 3 because we consider the function value. So substitute x by 3 minus 1, 3 minus 4 divided by 9 minus 1, 9 minus 4. Clear? Multiply y2. Okay? Okay, now you see, we just consider the numbers. Okay? Then we can obtain. Okay, of course, I omit the details, right? It's okay, because just the numbers operations. Okay, finally, you can practice to check. Okay, the final answer is 1.70000. Okay, so that means now you see, we just use 1.7 to approximate square root 3. Of course, we know we have 2 significant digitals. It's okay? So this is a method to compute the function value. Okay, square root 3. Square root 3 is a irrational number, right? Okay, we need to find its float number. Okay, or approximate number. Now you see, we can use the interpolation polynomial. Okay, to approximate the square root 3. See, it's okay? And also here, we need to consider the error. So now we consider the error term. So R2x, because we focus on 3 when x equal to 3. So here we replace x by 3 directly. So R23 actually it is square root of 3 exact value minus the approximate value P2 3. It's okay? Okay, so in this case, because we are given the function, this is also fx, right? Fx equal to square root of x. Okay, so let's use the error estimation here. Now you see, this is the remainder term. So we need to consider the n+1th order derivative of f at c divided by n+1th fraction number. Because here we consider just 3 nodes, so we need to consider here. Okay, n+1, n equal to 2 here. It's okay? This means n equal to 2. So n+1th order derivative, so here is 3. Third derivative of f at c, right? At c divided by n+1, 2+1 fraction number, and multiply, don't forget, multiply x minus x0, x minus x1, multiply x minus x2. It's okay? So here x is 3. Okay, x0 is 1, x1 is 4, x2 is 9. So 3 minus 1, 3 minus 4, 3 minus 9. It's okay? So we can compute these numbers, right? Okay, then here we can obtain the error by the absolute value. By the absolute value, the error can be bounded less than or equal to. Okay, of course here, actually, let's consider because fx is square root x, that means x the power is 1/2, right? Okay, so first derivative should be 1/2 multiply x 1/2 minus 1. It's okay? So it is minus negative 1/2. It's okay? The first derivative. Okay, the second order derivative. If we consider the second order derivative, it should be 1/2 multiply minus 1/2 multiply x minus 1/2 minus 1. It's okay? You should familiar with this computation, right? Derivative. So it should be minus 3/2. It's okay? This is a second derivative. Clear? And now we need to consider the third derivative. So again, it should be 1/2 multiply minus 1/2 multiply minus 3/2. And here should be x minus 5/2. It's okay? Because minus 1 again. So minus 5/2. It's okay? And now, because we just consider the upper bound, and actually we don't know where is c, but we know this function is monotone function, right? It is monotone function, and we know the maximum number is at 1. It's okay? Because the power is negative, right? The power is negative, so the maximum number should be when x equal to 1. It's okay? X equal to 1. So now don't forget, here we have 2 plus 1 fraction number. 2 plus 1 is 3. 3 fraction number, right? Okay, here I write here. 3 fraction number should be 6, right? So that means we have 1/6 firstly, the denominator 1/6, this term, okay? And this is this term 1/2, this term. Okay, multiply, don't forget absolute value. So absolute value, so that means absolute value c less than 1/2, multiply this 1/2 and multiply 3/2. Okay, because when x is 1, it is maximum number, right? So here, 1 over 2, 1 over 2, 3 over 2. It's okay? It's okay? This 1 over 6 means this denominator. Okay, and then here should be 3 minus 1, it is 2. Okay, 3 minus 4, it is minus 1. But by absolute value, it is just 1, right? And 3 minus 9, minus 6. By absolute value, it is 6. It's okay? So I show you the details. Okay, of course, you can practice. Okay, the product, finally, the product is 0.75. 0.75. Okay, so that means we estimate, okay, square root. Okay, I write here, square root 3 by 1.7000. Okay, if we choose, okay, 1, 2, 3, 4, 5, 6 digital, but we only have 2 significant digitals, right? 1 and 3, 1 and 7, 1.7. And also we know, that means we know the exact value minus the approximate value can be bounded by the error band. Error band here is 0.75. See, we obtain the approximate value and also we estimate the error. Clear?